All right. Good morning, everybody. Welcome back. So for today, um, let's continue talking about covalent bonds. That's where we stopped on Wednesday. So if I ever see you somewhere and I don't recognize you, I cannot do much about that because I don't know what you look like. And if you want to stop by my office, I'm on campus every day on Sci A377. So the building here is open Monday through Thursday. Okay, so let's see where we stopped. Okay, so we are talking about covalent bonding. This is a kind of bond that is based on sharing electrons, okay? So once a pair of electrons is shared, this pair will belong to both elements involved in the bonding. We can have a single bond where one pair is shared, a double bond where two pairs are shared, or a triple bond where three pairs are shared. We are going to use the Lewis notation. So the Lewis notation, we have the symbol of the element and the number of valence electrons around the element. Okay, each valence electron is represented by a dot. So we have here one dot because there is just one valence electron, 2, 3, all the way to 8 dots here, which is the max. All right, so now let's start thinking about building Lewis structures for covalent compounds. So we are going to follow here a sequence, and there are some things to help us to decide what kind of bonding are we going to have in our compound. The first step is to count the total number of valence electrons, okay? Each element that forms the compound brings a number of valence electrons. So we are going to add all the valence electrons for each element in the formula. So that's our first step. After that, we are going to verify and account for charges. If the compound has a negative charge, electrons are going to be added to the total number. If the compound is positive, electrons are going to be subtracted from the total. Third step is to choose the central atom. The central atom is usually the element in the lowest amount in the formula, or the larger element in the compound. There are some exceptions, but this accounts for 95% of the cases. And then fourth step, we are going to connect the atoms using covalent bonds, and this connection can be a single bond, a double bond, or a triple bond. After we connected the atoms using the valence electrons, if there are electrons left from the total, then we are going to distribute among the atoms to fill the octet. We are going to start from the atoms on the outside of the structure, moving to the central atom. And remember, our goal is to have 8 electrons in the valence shell for all the atoms, except when we have hydrogen. For hydrogen, 2 electrons is all you need to achieve stability. Okay, and here, let me show you the Clark's rule. The Clark's rule is really, really useful, and it will tell us if we have only single bonds, if we have a double bond in the compound, or a triple bond. For the Clark's rule, we are going to compare X and the total number of valence electrons, including charges. X is 6 times the number of non-hydrogen atoms plus 2. Okay. So we are going to compare X with the total number of valence electrons for the compound. And we have 3 possible cases here. If X is equals to the number of valence electrons, we only have single bonds in the compound. If X minus the number of valence electrons is equal to 2, then you have 1 double bond in the compound. And if X minus the number of valence electrons equal to 4, then you have either 2 double bonds or 1 triple bond. And we will have to decide between the 2. All right, so the best thing to do to understand these ideas here is by doing an exercise. So let me do this together, and then I will show you step by step what I mean for each of those steps here. So let's draw the Lewis structure for CH4. This is the methane gas. So formed by carbon and hydrogen, so therefore it's a covalent compound. Okay, so let me switch to my other screen here, and I can make some notes. All right, very good. So let's start counting the total number of valence electrons. So we have here CH4, 1 atom of carbon and 4 atoms of hydrogen. So you always should have a periodic table next to you to help you to find the number of valence electrons. So the total number of valence electrons, it's going to be equals to the number of valence electrons for each atom added up over the structure. Carbon belongs to the group 14, so therefore it has 4 electrons. And attention here, we just have one atom of carbon, therefore times 1. Plus the number of valence electrons for hydrogen. So that's very easy, 1 electron. However, we have 4 atoms of hydrogen, therefore we have to multiply each valence electron by 4. So always, always, always multiply the number of electrons by the number of atoms that you have in the structure. So that gives us 8 electrons. Okay, so 8 electrons is the total number of electrons in the compound, and I'm going to use those 8 electrons to connect all the atoms in the structure. Step number 2 is to account for charges. This compound is neutral, so therefore we don't need to add or subtract any number from the total. If the charge is negative, that means the compound has an excess of electrons, then you will add the number of the charge to the total number of electrons, and vice versa, okay? If it is positive, you are going to subtract. The third step is to choose the central atom. And here is one trick. Hydrogen cannot be the central atom in any case, okay? Hydrogen will never be the central atom. So the central atom is usually the element in the lowest amount in the formula, and also usually the larger element that you have in the compound. So we know here that, therefore, carbon has to be the central atom, and we are going to have the hydrogens surrounding the carbon. Okay, so let's draw here. Hydrogen, hydrogen, and hydrogen. Okay. How are those atoms connected? Are they connected through single, double, or triple bonds? So to figure that out, to have an idea, now let's use the Clark's rule. So we are going to compare X and the total number of electrons. So I'm going to write right here in this part of the slide here. X for this compound is 6 times the number of non-hydrogen atoms, which is just 1 plus 2. Therefore, X equals to 8. And now we compare X with the total number of valence electrons for the compound. So in this case, X equals to 8, and the total number of electrons in the compound is equals to 8. So therefore, we have the first case, which means we only have single bonds connecting the atoms in this structure. Okay. So now that we know that carbon is the central atom, 4 hydrogens surrounding the carbon atom, and we only have single bonds, the next step is to connect the atoms. Single bond means that 2 electrons are shared, 1, 2, 3, and 4, 5, and 6, 7, and 8. Okay, so each single bond uses 8 electrons, which was what we started with. So therefore, there are no leftovers of electrons. So we stop here. Now let's count how many electrons each element has and see if we filled up the octet or we filled up the duet for each hydrogen. For each covalent bond means that the two electrons belong to the two elements involved in the bond. So if we count the number of electrons that hydrogen got is 1 and 2. So therefore it filled up the duet, so that's stable. Is the same for all hydrogens, so we don't need to count again. And let's count how many electrons carbon has. 1, 2, 3, and 4, 5, and 6, 7, and 8. Okay, so therefore the octet for carbon is also filled up. Everybody is happy in this compound, therefore we stop here. Another way to represent the covalent bonds, and it's actually a better way, is to represent each covalent bond by a trace. So we have here CH, CH, and CH, and that's a better representation, and it will take less space than drawing the dots.
Excuse me, George.
Yes.
What would it look like in a situation where not all of those things could be checked off?
That's the next example.
Okay.
Yes. So usually here the problems will arise when you have a charge. So that's the first thing that may happen. And then for number 5 here, if you have leftover electrons, so then we have to deal with that. And give me 1 minute and I will show you the next example. Thanks, Holly. Okay, so let's move on now to a slightly more complex example. So when we have the CO3 2-, so that's the ion carbonate. And the goal here is to draw the Lewis structure for this anion, okay? So we have carbon and oxygen, therefore this is a covalent compound. Electrons are being shared to fill up the octet for all the elements in the structure. Our goal is to determine how the electrons are being shared between the atoms. Is either just single bonds, double bonds, triple bonds? Do we have any electrons that are not bonding to anyone? So that's what I want to show you with this example. So everything starts counting the total number of valence electrons for the structure. So we have here carbon, and always pay attention here, 3 oxygens and 2 negative charges. So therefore, the number of valence electrons, or the number of total electrons in this case, is going to be equals to. So carbon brings 4 valence electrons because belongs to the group 14. We only have 1 atom of carbon, so times 1, plus oxygen belongs to the group 16. Therefore, we have 6 valence electrons. Attention here, we have 3 atoms of oxygen, so we are going to multiply by 3. And in this case, we have a charge. This charge is negative, and the magnitude of the charge is 2. So we have to account for charges in this case. Because the charge is negative, that means electrons are being added. So we are going to add, okay? So here, adding electrons. And the number that we are going to add is exactly the magnitude of the charge, 2. Okay, so if there is a negative charge, that means electrons are in excess, and we are going to add exactly the number of the charge. So for CO3 2 minus, we have here 6 times 3, that's 18, plus 4, that's 22, plus 2, that is 24 electrons. Okay, so this compound has a total of 24 electrons, and I'm going to use all those electrons to connect the atoms. And if there is any left over, we are going to find a way to distribute that. So therefore, be very careful with charges. So the next step is to choose the central atom. Here, there is no mystery. We have carbon as our central atom, is the largest element between carbon and oxygen, and also is the element that you have the lowest amount in the compound. Carbon is going to be surrounded by oxygens. So I'm going to draw here as a triangle. So it doesn't matter for now where you position the elements around the central atom. Okay, so now that we got all the way to this point, we need to connect the atoms. Are we only going to use single bonds? Do we need a double bond or a triple bond? Let's use the Clark's rule to determine what we need. So I'm going to write here on the right bottom corner of the slide. For the Clark's rule, we are going to determine X first. X is equal to 6 times the number of non-hydrogen atoms. In this case, we have 1 carbon and 3 oxygens, therefore 4 plus 2. 6 times 4, that's 24, plus 2, that is 26. And now we are going to compare X with the total number of electrons that we already calculated here, and it is 24. Obviously, in this case, X is not equals to the number of total electrons. 26 minus 24, that is equal to 2. So we are in the middle case here. When the difference between X and the number of valence electrons is 2, then we need 1 double bond. Okay, so we will always have a single bond because we have to connect the atoms. And in this case, one of the connections between carbon and oxygen is going to be a double bond. So let's connect all the atoms using a single bond to start with. So one single bond here, one single bond here. And then for one of the carbon-oxygen bonds, I'm going to use a double bond. I am picking the oxygen on the top of the structure, but it doesn't matter which one you pick, okay? So all of them are equivalent. That's how the Clark's rule will help you figure out if you need only single bonds, a double bond, or a triple bond. Okay. Does that partially answer your question?
Could you explain one more time where the 26 minus 24 came from?
Yes. So look here at the right side of the slide. See here Clark's rule. Okay, cool. So for the Clark's rule, we are comparing X right here with the number of valence electrons. Okay, so this rule has no scientific background. Okay, it's something that Clark figured out that works. Okay, so it's something empirical, let's say, and it really works. For 99% of the cases, it really works. It's really precise. Okay.
Are you going to present us with the other 1%?
Of course, it's coming next week. For this week, all the cases will fit within the Clark's rule. Okay, and then I will show you, I think I know 2 exceptions among all the structures, and then we will cover that. Okay, so when I'm calculating X is 6 times the number of atoms that are not hydrogen. Attention with that. You are going to count the atoms that are not hydrogen. In this case, we have 4. 6 times 4 is 24, plus 2, that's 26, and that's the number right here. And remember that 24 came all the way from here. And with that, I know that there must be one double bond. And I picked the double bond to be between the carbon and the oxygen at the top of the structure. It doesn't matter the position of the bond, okay? So it must be there. You pick whatever carbon oxygen you want to fill up the double bond. Okay, so now let's count how many electrons I needed to use just to bond the atoms, just to connect the atoms. 1, 2 for one single bond, 3 and 4 for the next single bond, 5, 6, 7, and 8. Okay, so just to bond the elements, I spent 1, 2, 3, 4, 5, 6, 7, 8 electrons. See here that I started with 24. So that was my total, 24. And then to connect the atoms, 8 electrons were spent. That means there are leftover electrons. 24 was the total. 8 was what we spent connecting the atoms, which means we have 16 electrons left. So we have to do something with those electrons that are left. And what we are going to do is to distribute among the atoms to fill the octet, to complete the octet. We always start with the atoms from the outside of the structure and move towards the central atom if there are electrons left. Okay, so here is the strategy that I'm going to use to distribute the 16 electrons left. I'm starting with the oxygen here on the left corner. Count how many electrons this atom has and how many it needs to complete the octet. Remember, each single bond means 2 electrons that belong to both elements. So therefore, this oxygen has only 2 electrons. Of course, it's not happy because it needs to have 8. So let's add 6 electrons around the oxygen to complete the octet. 1, 2, 3, 4, 5, and 6. So now if you count how many electrons this oxygen has, we are going to count 1, 2, 3, 4, 5, and 6 that were added, 7 and 8 from the covalent bond. Therefore, we filled up the octet. So now this atom is good to go. 8 electrons in the valence shell achieved stability. Now let's move counterclockwise and take a look at the oxygen on the right corner here. It's the same situation as the oxygen on the left. We have 2 electrons, so that therefore it needs 6 to achieve stability. 1, 2, 3, 4, 5, and 6. 7 and 8. Now this atom is stable. And finally, let's take a look at the oxygen at the top of the structure. This oxygen has 1, 2, 3, and 4 electrons from the double bonds. It's not 8, so therefore we need to add 4 more electrons to complete the octet. 1, 2, 3, and 4. So now this oxygen is with the octet filled. So therefore achieved stability. And finally, let's count how many electrons the carbon has. 1, 2 for the first double bond, single bond, 3 and 4 for the second single bond, 5, 6, 7, and 8 with the double bond. So therefore, carbon, because it has 2 single bonds and 1 double bond, achieved stability with 8 electrons in the valence shell. And let's see if we used the 16 electrons that were left here, 2, 4, 6, 8, 10, 12, 14, and 16. So therefore, the 16 electrons left were used to fill up the valence shell for the oxygen and achieve stability. Another way to represent this structure is drawing the bonds as a solid trace. For the single bond, it's just 1 trace. The double bond, we are going to add 2 traces. And I want you to always represent the electrons that are not bonded as well. The electrons that are not bonded, not being used to make a bond, they are called lone pairs or non, oops, bonding electrons. Okay, so any pair of electron that is not is not being bonded to anything is called lone pair or non-bonding electrons. And I want you to always represent them in the structure of the compounds. Okay, so CH4 was a simple structure where we didn't have any charges and we didn't have any electrons left over. So therefore, there is not much secret to draw the structure. Carbonate is more complex, where we have to account for charges and we have leftover electrons after making the covalent bonds. So when you have leftover electrons, start filling the octet for the atoms on the outside of the structure. And if after that you still have electrons left, you are going to start moving those electrons to the central atom, okay? At the end, all the atoms need to have 8 electrons. Remember, each covalent bond means that the electrons belong to the 2 elements involved in the bond. Oops. Okay, so follow the steps and understand what you are doing in each step, and then you should be able to solve most of the structures. Again, this is a matter of practice, and we are going to get some practice next week as well. Let me see here if I have, yes. Okay, I have one more example here for the PCl3. I'm going to give you a couple minutes, try to start setting up this problem, and then we will solve it together. Okay, so let's start solving this problem. So our goal here is to draw the Lewis structure for PCl3. So the first step is to count the total number of electrons, okay, of valence electrons. Let's draw here. Number of valence electrons is going to be equal to. Okay, so phosphorus belongs to the group 15, therefore 5 valence electrons. We only have one atom of phosphorus, therefore times 1, plus chlorine, group 17, 7 electrons. However, we have 3 atoms of chlorine, therefore you must multiply by 3. So that's going to be 7 times 3 is 21, plus 5, that is 26 electrons. Okay, so this is the number of electrons that we have in total that's going to be used to connect the atoms, and if there is any left over, to complete the octet for all the elements in the structure. Now, let's use the Clark's rule to give us an idea if we have only single bonds, if we need a double bond, or if we need a triple bond. The Clark's rule is going to compare X with the number of valence electrons. X is 6 times the number of non-hydrogen atoms. 3 plus 1 is 4, plus 2. 6 times 4, that's 24, plus 2, that is 26. Now we compare X with the number of valence electrons that we already determined. So we have here 26 is equals to 26. Okay, so one of the 26 is coming from the first step, and the other 26 is X. When we have X equals to the number of valence electrons, we have here the first case, which means there are only single bonds connecting the atoms. Okay, so now that we know the number of valence electrons and that the atoms are only connected using single bonds, the next step is to draw the structure. Central atom is usually the largest atom in the structure. In this case, is phosphorus, surrounded by the 3 chlorines. Doesn't matter which position you pick the chlorines to be at this point. It will be important later. It matters that phosphorus is in the center and this is surrounded by 3 atoms of chlorine. Now let's use the 26 electrons to connect the elements. We know that there are only single bonds. One single bond here, another single bond on the left side, and another single bond on the right side. Okay, to make the 3 single bonds, we spent 6 electrons, 1, 2, 3, 4, 5, and 6. Remember, 2 electrons for each single bond. However, we have a total of 26 electrons. Therefore, we have 20 electrons left over. What we are going to do with the leftover? Start filling the valence shell starting from the elements on the outside, moving to the central atom. Why I'm starting from the outside? Because on the outside, we have the smallest elements, and they will attract easier the electrons than the large central atom. Okay, so let's start with the chlorine here on the left. It has only 2 electrons from the single bond, so we need 6 more to fill up the octet. 1, 2, 3, 4, 6. 1, 2, 3, 4, 5, 6, 7, 8. So that's good. Moving on counterclockwise. The same thing for the other chlorine. So only 2 electrons here. So therefore we need 6 more. Now we have 1, 2, 3, 4, 5, and 6 lone pairs, plus 2 from the single bond that filled up the octet. And now the chlorine on the top of the structure is the same thing. 2 electrons, we need 6 more around to fill up the octet. So now it's good. So let's see if there are any electrons left over. So just to fill up the octet of the chlorines, we spent 2, 4, 6, 8, 10, 12, 14, 16, 18. So for the chlorines, we used 18 electrons. We had 20, therefore there is still 2 left over. Any leftover will be sent to the central atom. 1 and 2. Now let's count how many electrons the central atom has. 1, 2, 3, 4, 5, and 6 with the 3 single bonds, plus 2 lone pairs, that is 8. Okay, so see here that with the leftover electrons, I completed the octet for the element. We can draw this structure in a more organized way, representing each single bond by a trace and drawing the non-bonding, the lone pairs around the atoms. So we have 3 lone pairs around each chlorine and 1 lone pair around the phosphorus. And this is how you are going to draw the Lewis structure for covalent compounds. Okay, so the Clark's rule will help you to figure out if you need double, single, or triple bonds. Count the number of electrons. If there are leftovers, start filling from the elements on the outside. And then if there are still leftover electrons, just dump them in the central atom. Okay, and that is right on time. So that's the point I stop. And I hope you have a good weekend, and I will see you next week on Monday. Bye-bye.
Thanks, George. Have a good weekend.
Bye.
Thanks, Professor.
Thank you. Have a nice day.
Bye.